Welcome everybody to this AJS seminar. This seminar will be recorded. Today's speaker is Dario Andrini, and will talk to us about optimal design of planar shapes with active materials.
Okay, thank you. So, as Francesco already read, this is the title, Optimal Design of Planar Shapes with Active Materials. So, first I will make a brief introduction of what do we mean by active materials and why are they important in applications, and then I will move to the more technical part, in which I will discuss my joint work with I've done with my supervisors Alessandro Lucantonio and Giovanni Noselli. So first I would like to introduce you to the topic of shape morphing. Shape morphing is the discipline which essentially studies shape transformations of real material objects. So generally we study natural organisms because for living organisms it's very important to being able to perform functional shape changes which are necessary for their life. So for example, it's interesting to study how plants, flowers, trees grow, and how do they morph themselves. And but this is also important for in applications. So okay, so somehow understanding how nature's controls the morphing of plants and living organisms, it's important for being inspired and build new generation of, for example, robots. So here we're talking about the new emerging field of soft robotics, where the aim is to build to devices which are able to perform functional shape changes. However, these soft robots are different from the classical robot we have in mind. They are not built with discrete components, rigid and linked by motors. In this case, what drives the shape change is what we call internal activity. So somehow the driver of the shape changes is encoded in the properties of the material itself. So these are, for example, two examples of artificial morphing. These are active materials. In particular, on the left we have hydrogels. On the right, pneumatic elastomers. All these bodies were initially flat, and upon an external stimulus, they were able to change shape in this fancy way. So we have spoken about active materials. So more in detail, active materials. What are active materials and what is internal activity? In this image, I reported a wall of plant cells. So these are alive, and being alive, they are able to grow, to change in size, and to change shape. So the combination of all this, the shape changes of each cells macroscopically results in the growth of a flower. On the artificial side, I've already mentioned hydrogels. Hydrogels are constituted by a polymer network cross-linked in a proper way, so they behave like sponges. So they are able to absorb fluid, solvent, and this absorption translates into an increase in size, which can be locally controlled, and if done in a proper way, can result in some shape transformation. For example, these saddle-like discs, or even more complicated shapes. So now the aim is to understand how to model internal activity thematically, and we would like to do it in a general and abstract way, in the sense that we don't want to stick to a particular mechanism that leads to activity, but we want just to control activity in a wider, to describe activity in a wider sense. So first of all, I will make a brief introduction of the notation I will use and continuum mechanics in general for passive materials, and then I will generalize to active materials. So suppose we have a body which we name B. And this is what we call reference configuration. And this reference configuration is supposed to be at rest. At rest in the sense that we imagine that no external forces are acting on the body, so no internal stresses are present inside the body. Now imagine that we squeeze it, we apply some forces, then it will deform according to a map, deformation map that we denote by F. As a notation, we generally use this notation. So capital F is the gradient, the spatial gradient of the deformation. Now, this new configuration is referred as current configuration, and it is stressed. So we have squeezed the body, so internal stresses arises. And how to account for this, we have to introduce an elastic energy density. And from once one has the energy, can compute the associated stress tensor S, which is this in the case is the first Kirchhoff stress tensor. Okay. Now, in general, to describe rest and reference configuration and curve configuration, it's useful to rely on the Cauchy-Green strain tensor that I will introduce, which is nothing else but the pullback of the Euclidean metric through the map F of the body B. So one takes two, say, tangent vectors to B, consider their mapping through the differential, and then one computes the scalar product of Fu times Fp, and defines with these simple passages the Cauchy-Green strain tensor, which is indeed a metric tensor. So an easy remark that will, however, important to understand not the mathematics, which is somehow standard, but the mechanical meaning of these objects. So if we have, let's see, it's equal to the identity, then one upon integration can recover the deformation map. And seeing it is the identity when one understands that it is a rest configuration. Of course, if one has a general C, then integrates and finds F, so we are in a stress configuration. So in this case, we have an association between a configuration and a metric tensor. Indeed, these are passive materials, as I said. For active materials, it's not appropriate to describe the rest configuration with a map or with a rest reference configuration. What is appropriate is to describe it with a metric tensor. Okay, so in order to understand it, to get a feeling of that, I'll make this little toy. So suppose that we have our body. We consider two infinitesimal elements inside of it. And let us zoom and imagine, let us make a mental experiment, the experiment. So we imagine to isolate these two elemental volume from the surrounding materials. Now we switch on activity, and what happens is that the new relaxed state, so stress-free configuration, is this one. So each material element has changed shape somehow. So activity is a local prescription of a relaxed state. However, now we have to understand if this new relaxed state corresponds to a configuration, so a configuration of our body or not. And in particular, we ask if residual stress arises from the incompatibility due to activity. So the new formulation that one has to adopt for active materials, could adopt for active materials, is the following. Our body B again, and then we prescribe a target metric tensor which describes the rest state of the body, and we denote it by C bar, and it is generally referred as target metric. This is prescribed in an arbitrary way, and it is dictated by the activity process. So in principle, it could not be integrable. So there is not an associated map to that. So there is not a configuration, a relaxed configuration associated to this rest configuration. So the answer, the question is, what is the real configuration that the body will adopt? Is it stress-free or not? So the answer to find the F in red is elastic energy minimization. So one has to take the energy. The energy is a function of C in red and C bar in green. So C is the real deformation and C bar is the target metric prescribing the relaxed stress. And of course, if there is a match between the two, if C is equal to C bar, then it means that it is integrable. And so the elastic energy is zero, because this means that the configuration described by the map F is integrable, and so can be realized. So there is a stress-free configuration in this particular case. So again, one minimizes the energy, finds F. So I've already made this remark. So if C is integrable, then one integrates this C bar, finds F, and then F is trivially the stress-free solution of our problem. So this is to introduce how we generally model internal activity. Okay, now we are ready somehow to introduce the problem, the real problem we want to study, which is this one, optimal shape design. So we have okay, there's a mistake. Omega is not omega, but is B. I've corrected that. Okay, so imagine that omega for the moment is B, capital B, what we have introduced before. So the goal is to control internal activity. So what we have introduced, the target metric, in order to deform in an optimal way the body, which has initial shape gamma. The shape for us is the boundary of omega, which morally is B. So that the final shape that we reach is close to a target shape gamma. So we want the initial domain to be close to the orange curve that we draw. Of course, the closer we are, the better it is. Okay, so there are three ingredients to introduce. So we have to introduce the mechanical model, we have to introduce a notion of optimality, and a notion of distance between shapes. The distance between shapes. So, first of all, mechanics. So we have already introduced the notion of activity, but now we have to be a bit more precise. In particular, we will make some approximation. Our body is not doesn't have a generic shape form, but it is a cylindrical body with cross section omega and height h. And we assume that no traction are present on the boundary, so no one is pulling on the boundary in this object, and no gravity body forces are present. No body forces are present. Moreover, we assume that the target metric, the activity, has a particular structure, a particular pattern. So it is there is no activity on the longitudinal, the vertical direction. The activity is concentrated on the plane, the planar direction, and the metric is invariant along the height of the cylinder. This assumption simply allows to transform the three-dimensional elasticity problem into a two-dimensional elasticity problem. So from now on, all our equations will be defined on a two-dimensional domain, which is the cross-section of the cylinder omega. So these are the equations for the mechanical equilibrium, which are now written in weak form because it will be useful later. Just stress that this is where target metric enters into play, written in red. Okay, the second ingredient is to define a notion of distance between shapes. The notion of distance that we adopt is the classical Hausdorff distance, which is defined in this way. Just a remark that this distance is not suitable for our purpose, in particular for numerical implementation of the problem, because of the sup and inf operators, it doesn't admit a shape derivative. Indeed, we want to use a gradient-based optimization algorithm, so we need this derivative. And we found in literature that there are present smooth approximation of these distances. And so, for example, and indeed in the numerical implementation, we use a differential approximation, which is this dh tilde, where the sup and inf operators are approximated with integral according to this principle that for which the LP norm converges to the L infinity norm. Third and last ingredient is the notion of optimality. We have to define this, we call it complexity function, the calligraphic C, which is an integral of a density which depends on the target metric and its gradient. We call it complexity because it is supposed to describe how the complexity of the pattern of activity that we want to introduce in our body. So minimizing that will mean to minimizing the complexity, to reduce the complexity of the activity pattern, which from an application point of view could be useful because one would like to produce a shape change in the simplest way. For the moment, we let this complexity function unspecified. We just assume that it is positive, actually non-negative, isotropic, which means that if I rotate the target metric, then the density doesn't change. So there is not a preferential direction. The complexity doesn't feel a preferential direction of productivity. And the last point, another mistake, sorry, this should be that the derivative of the density key with respect to the gradient is 0 for every g. So for every g, it is a stationary point when the gradient is 0. So in the sense, if our metric is uniform, it's better. Okay, so we have all the elements to introduce the optimal control problem we want to study, which is this one, which is minimizing the complexity plus a term which penalizes the distance between the transformation of the shape gamma, so f of gamma, and gamma bar, which is our target shape we want to reach. Everything is subjected to the constraint of mechanical equilibrium. Notice that we minimize on C bar, but also on F, where F runs on the set of all isometries in R2. This is because our problem, mechanical problem, doesn't have a unique solution because in this case we have null traction on the boundary, which means non-boundary conditions. So given a C bar, the solution is unique up to isometries. So we also have to minimize on isometry to get a meaningful problem. This is the problem that we want to solve. As already remarked, for numerical purposes, we need to introduce a smooth approximation of the Hausdorff distance, which is d tilde h. And so this is the problem that we will solve numerically. I remark the coefficient AD is chosen big enough in order to allow an accurate match between f of gamma and gamma bar. So, yes?
If I may just ask quick question. What is V?
What is
V?
the space?
Yeah.
Okay. We left it unspecified in the sense that the energy could be whatever. This is the first reason. The other reason is that in general we perform a formal calculation with no rigorous proof. So we left it unspecified.
Okay.
Okay, yes. It could be H1.
Okay.
Okay, so this is what we want to solve. Of course, the problem is very complicated, cannot be treated in its generality analytically. It needs numerics. However, something can be said on some special cases analytically. What is this special case? We need to consider a restricted family of shape changes, which we call affine shape changes. Given two shapes, gamma and gamma bar, we say that they define an affine shape change if there exists an affine map such that this map transforms one shape into the other. Okay. In order to treat this problem analytically with calculations, it's better to consider a slightly different problem with respect to the one I introduced, which is this one. It differs from the previous in the sense that the constraint of reaching the target shape is imposed exactly and not through a penalty in the objective function. So this constraint is encoded in this new space M, which is nothing else but the space of deformation, which sends exactly gamma into gamma bar. Okay, now we observe the following. These are affine shape changes, so there is an affine map sending one into the other. One can compute its associated metric tensor or Cauchy-Green strain, which is CA, and this is uniform, constant on the whole domain omega. Now, an admissible competitor for this optimization problem is C bar equal to CA. And it is a trivial competitor in the sense that the mechanical problem in this case is trivially satisfied and it is the stress-free problem. So what we ask is this C bar optimal? Okay, in order to answer that, we define this Lagrangian. So we take the complexity function C and use a Lagrange multiplier to impose the constraint of mechanical equilibrium and find the stationary points. And after some calculations, one finds a conclusion which is summarized in this proposition. This proposition is quite general in the sense that it's valid for a generic elastic energy and in principle a generic complexity function. It states that this homogeneous target metric C bar equal to CA is a stationary point if and only if one of two conditions holds. So the first one is that the outward normal n to the reference boundary gamma is an eigenvector of C bar. The second one is that the eigenvalues lambda I of the target metric and the eigenvalues mu I of this quantity, which is the derivative of the density, the complexity density with respect to the target metric, satisfies this relation. So, in order to better understand it, I have two examples. These are numerical tests that we performed in order to test the validity of the proposition. And the figure, let's say that the first row is a shape changes and the second row is another shape changes. These are both affine, and the affine map associated to that is the same. However, one is optimal, in the other, in one case, the uniform target metric is optimal, in the other case, it's not. According to the first item in this proposition, we have that in both cases, these are the eigendirection for the target metric. And in order to have optimality, we need the normals to the square, for example, to be eigenvectors. And indeed, they are in this case, because the normal are always directed along the direction of the eigenvectors. For the ellipse, instead, this is not true, because the normals to the circle constantly changes its direction, so it's not always an eigenvector. These tests were performed with this complexity function that I reported above here, and it simply takes into account penalizes the magnitude of the gradient, and it's different with the identity tensor. Okay, we also made a test to certify the validity of item 2 in this proposition, which is this one. We choose the eigenvalues, the eigenvalues of the affine map in a proper way in order so that this relation is satisfied, and we check if indeed the optimal solution was uniform, and the answer is positive. Okay. This is what concerns affine shape changes. So we can say something about that even without numerics. For the rest, we need to rely on numerics, and we made also numerical tests on different shape changes. In particular, we focused on these particular shape changes, which is the one depicted in subfigure A, which is a bending of a rectangular block. And we tested on these shape change with different complexity functions. So here we reported figure A is the shape change, and the plot represents the stress tensor. Figure B is a cut line along this this line of the component of the metric, and C, D, and A are the three components of C11, C12, and C22. This is the most basic case we tested, where we penalize just the gradient. And indeed, we see that penalizing the gradient leads to an almost flat profile for the C12, almost flat for E, and everything. So the real deformation is concentrated on C11, which is the activity along the horizontal direction. Then we also we tested, as I said, with different functions. So we take the functional before, and we add this term in red. This term, C bar dev, is the deviatoric part of C bar. So in this case, we are penalizing this quantity, which means that in this case, this quantity is 0 whenever C is alpha times the identity. So indeed, the optimization leads to a configuration. Let's look at figure C, D, and A, which is a conformal metric tensor. Indeed, C12 is almost 0, and C11 and C12 are almost identical. Okay, we know from the Riemann mapping theorem that there is always a conformal map in R2 sending the shape, the rectangular shape, into the bending. However, this is not a conformal map, it's just a conformal target metric. Indeed, it's not compatible, it's not integrable, because we see that some stresses arise. So, as could be predictable, stresses are a mean for reducing the complexity function, because there are more functions with stresses than stress-free function. Finally, we tested with this other complexity function. Again, we modified the previous one with this term, which penalizes the gradient of the maximum eigenvalues of the metric and of its minimum eigenvalue. And what is interesting for us in this case is that the optimization problem leads to a structure that in the limit could be a discrete structure. In the limit where this coefficient AG, which penalizes the whole gradient of C, goes to 0. And this reminds somehow phase transition when one has an interface which separates the two phases. And in this case, the two phases could be, we see that this red here has more or less the same value. Oh, sorry, another mistake. Believe me, this red here should have the same value of this red here, and same for the blue. So this means that this material, it's like a bilayer, so something composed by two layers of the same material, but the material is oriented in different way in the upper part of the layer and in the lower part. So in particular, the difference in orientation is 90 degrees. So this is more or less what we tested. And then we also checked if the algorithm was capable of dealing with more general shapes. And we tried this one, which is quite sharp, and the algorithm seems to deal quite good with also with complex shapes. So that's all. Sorry for the mistakes, and thank you for the attention.
Are there any questions also from the online audience? I have one question. Can you talk about more about the optimal control problem? I mean, what?
You mean
Yeah, in what phase do you from the optimization and like you parameterize your?
Okay, from the numerical viewpoint.
Yeah.
Okay. Okay. The optimization algorithm. Oh, sorry. The optimization algorithm is this one. No. Which is stands for sequential nonlinear optimization, and it is a library written in Python, which is also embedded in a commercial software that we use, which is Console. So we use Console both for the optimization part and for the solution of the mechanical problem. And the mechanical problem is solved with the standard finite element method. And this is a gradient-based optimization algorithm. So
anyway, you choose the solution in a finite element space.
What?
The solution is in a finite element space.
Yes. Yes. We use standard triangulation, nothing strange, and second order